this video, I'm going to give you some tips for working on Lab 8, the unknown alkene experiment. There are two parts to this lab. The first part is performing a series of chemical tests on one hexene. So all of these chemical tests, you're only going to perform on one hexene. You're not going to perform any of these tests on your unknown alkene. There's all of these different tests to perform, and then you are just going to record your observations in this little box. This box is intentionally small because I want you to be as brief as possible. You're going to want to be able to easily and quickly use the results from this experiment in a later experiment, something that we're going to do further on down the road. And the more little words that you fit into these boxes, the harder it is to interpret this information. So if you don't see anything happen at all, if there is no observable reaction, you could just write NR or maybe just put an X in the box or cross it out or something like that. If you do see a color change, just write the new color. So maybe just say that it turned blue, just write blue. And you don't need to be really descriptive about the color blue. Like I said, try to use as few words as possible. Maybe it bubbles or fizzes or something like that. So just try to be as brief as you can. You can always go back and redo these later on down the road if you decide that they're not descriptive enough. But like I said, it's going to be a lot easier for you to use this data if you have just one or just a couple of words in each one of these boxes. So moving on to the actual unknown part of this experiment, you are going to do the rest of this post-lab based on your unknown alkene. Everybody has a different unknown, so I'm going to be showing you data for my unknown alkene. It's probably not going to be the same as yours. And this set of data right here is the stuff that I copied from the software when I opened it up, so you'll be able to see all of this as well. I highlighted that this 251 is my boiling point, not a melting point. It does use BP for boiling point and MP for melting point. Although it's not really important that you make a note of which one that is. And you are going to want to convert that into Kelvin because the database that we use is going to be reporting the boiling and melting points in Kelvin, not in degrees C. So I'm going to do this in black. I've got my boiling point in Kelvin is 524. So the next thing that you're going to do is take a mass spec of your unknown, and I have got that right here. So we're going to take a look at this. Is my unknown mass spec, and what we want to do is find the molecular weight on the mass spec, which means that we want to be focusing on the cluster of peaks that are on the right hand side. So I'm going to zoom in on those. And this one's actually a little bit tricky because normally what we would do is look at the cluster of peaks on the right hand side. We would find the one that is the most abundant, and that peak right there we would take as our molecular weight. But this one, this particular mass spec has got a total of 3 peaks over on this side. This peak that's furthest to the right is typically our M+1 peak, unless we have a chlorine or a halogen present, bromine. So if that is the case, then that would make this my M+ peak, and this is just some random peak. This is kind of a confusing mass spec to work on. I am going to, you've got kind of a 50-50 guess. One of these two is definitely our molecular weight. And I'm going to just sort of pay attention to what we're looking at here in terms of their masses. So if this is 120, 25, 30, 35, 40, no, 25, 30. What's the increments here? 1, 2, 3, 4, 5. So each one of these corresponds to 4. So this is 124, this is 128, this is 132. Let me just double check that that's right, 136, 140. So that would mean that this peak is 131. Now I have a couple of options here. I could just kind of go with the principle that the highest peak is the molecular ion, and I could say this is my molecular weight, 131, but I could kind of put a question mark by it. Keep in mind that if my interpretation doesn't work out, if I get stuck, that I should come back and try all of my calculations again using 132 as my molecular weight. And to kind of help me remember that, maybe it would be helpful for me to write 131, 132. I'm not 100% sure which one it might be. Now, my instincts are telling me that it is most likely 132, and there's two real reasons for that. The first one, which I already talked about, this would be my M+1 peak, the smaller peak over here, which would make this my M+ peak, this guy right here. The other hint that I have, is, if you remember, molecular weights are typically even numbers. Unless there's a nitrogen present, which isn't very common, my molecular weight should be an even number. So my bet is that the molecular weight is 132, and I'm going to kind of, proceed with that plan. But I am going to keep in mind that I'm not 100% sure about what it might be. So I'm going to actually change this to say 132. And then I'm going to make a little note to myself over here. It might be 131. And like I said, if I'm making my way through this assignment and I'm getting really stuck and having a hard time interpreting it, then I'm going to come back and try everything again using 131. Next thing I want to do is take a look at the IR. So let me get my IR open. Here it is right here. Now, of course, I'm expecting to see a peak that would correspond to a carbon-carbon double bond because this is an alkene. And that's probably this peak right here. Carbon-carbon double bonds are really sharp. They're around 1600. Looks like that. But what other information, I guess I could write that down. What functional groups do we have? Well, I know I have a carbon-carbon double bond. I knew that before I even looked at the IR. But what other functional groups can I see? Of course, I'm going to ignore everything to the right of 1500, so I'm just going to zoom it out of view. Take a look at this peak right here. This is around 1700. It's a little under 1700. So this is, I'm not sure. Should I interpret this as a carbonyl group? Maybe. It's possible. Real data can be kind of tricky. Another thing that I can see, and hopefully you see this as well, the absence of strong peaks in the 3000 area, which is typically a good indication that I have a benzene ring. So I'm going to sketch the benzene ring in as a functional group. And I'm going to keep a question mark by my carbon-oxygen double bond only because this is a little bit low. Although this one is operating on a logarithmic scale, if you notice the increments are in 200 wave numbers, but they get larger as you move from left to right. The increments get larger. So this peak possibly is at 1700. I could probably go back to the software and click on this peak and get the exact wave number. So maybe I have a carbonyl group, maybe I don't. Next thing that I'm going to do is come up with, so it says, any additional percent composition data for your unknown. So the lab is going to give you the percent carbon and the percent hydrogen, and if they do not add up to 100%, which mine don't, that means that there is another atom present, not just carbon and hydrogen. And what might that atom be? So since mine do not add up to 100%, I'm going to see what I have left. 100 minus 81.79 minus 6.1. I have an additional 12.11% that is not carbon or hydrogen. And I need to take a guess about what that might be. Well, I know for sure that it is not chlorine or bromine because I don't see that in the mass spec. I didn't see it in the mass spec. My gut is telling me that it's probably a carbonyl group and that I do have oxygen present, although it is possible that I have a nitrogen present and that odd molecular weight. So I've got kind of two options here of which way I should go with this. I'm going to stick with my initial suspicion that the molecular weight is 132. And then I'm going to say because of that peak in the IR, I'm going to assume that it's an oxygen and that my difference in a percent composition is coming from an oxygen atom. But again, I should probably highlight these questions. If things don't work out, maybe I'm going to have to come back and reevaluate. So maybe it's a nitrogen. And I'm just going to highlight these things so that if I do have to come back, if I do get stuck and I can't find the right structure, then I'm going to come back and reevaluate. Okay, so next, I'm going to use the molecular weight, functional groups, and the rule of 13 to come up with a molecular formula. So this is going to be based completely on the idea that my molecular weight is 132 and that I have an oxygen atom present. Now this one is kind of tricky because I'm going to assume that I only have one oxygen atom with one carbonyl group, but it is possible that I have two oxygen atoms and one of them is just not visible to me. I'm going to start by thinking that I have one oxygen atom and see what I get. 132 minus 16 is 116, and then I'm going to apply the rule of 13, which gives me 8.92 carbons. I'm going to round that to 9 carbons. So if I have C9, how many hydrogens do I have? 132 minus the oxygen minus 9 times 12 gives me 8 hydrogen. C9H8O. And we should probably do an HDI, well, that's coming up down here. I'm like, I really want to do an HDI calculation right now because this is kind of stressful to me. I'm not loving that, but we'll get to that. Verify the molecular formula by calculating the percent composition of each element. So what I'm going to do is calculate my percent carbon based on C9H8. So that would mean that I have 9 carbon atoms in a total of 132 for the molecular weight. Multiply it by 100 to make it a percent, and we'll see what we get. 9 times 12 is 108, divided by 132. That's 81.8% carbon. Let's compare that to what we got in the lab. That's really close. 81.79 versus 81.8 is basically the same thing. So this is actually looking pretty good. If I'm going to go ahead and do the rest of them before I celebrate. For the hydrogen, we have 8 hydrogen, molecular weight of 132. 8 divided by 132 is 6.1%. Let's compare that. That one looks perfect. And then the oxygen, percent oxygen, 16 divided by 132. This one has to work out since the other two worked out. 12.1%. Okay, so what this means is that I'm almost certainly correct with this molecular formula. And what that means, since this molecular formula is almost definitely correct, and the reason that I know that is because my molecular or my percent compositions matched up. So this is almost for sure the correct molecular formula, which means that the molecular weight is 132, not 131. And I do have oxygen present, not nitrogen. If these percentages had not matched up with what was reported in the lab, then that's when I would go back and I would try the 131 and I would try this being nitrogen instead of oxygen. That's where I'd try to see what I needed to adjust on this page in terms of that data. So now we're ready to calculate the HDI based on our C9H8O. 9 carbon atoms times 2 plus 2 is 20, minus 8 is 12, divided by 2 is 6. An HDI of 6 is more than what I was expecting. I was expecting an HDI of 5. I was expecting 4 for the double bond, or for the benzene ring, and then 1 more for the carbon-oxygen double bond. So I do have 1 more unsaturation, and I'm not exactly sure where it's going to come from, but I guess we'll find that out. Next, we're going to take a look at the H-NMR spectrum and report what we get from that. So let's pull up our proton NMR. Here it is, and my peaks are all pretty jumbled up here, so I do have some zoomed in view of all of this. But the first thing that I'm going to do is just report the types of hydrogen atoms, which I'm going to get from the number of peaks. So I've got 6 peaks here, which means that I have 6 types, and I'm going to use the same numbering system as what's in the software. So 1, 2, 3, 4, 5, 6, and I'm going to start by analyzing my integrals. So for analyzing the integrals on this software, this is real data, which means it's going to be a little bit trickier to work with than what we are used to working with. But what I'm looking at here is that I've got 4 that are all around the same 55 to 60-ish. And I'm going to just kind of say that each of these corresponds to 1 hydrogen or 1 proton. And then these 2 are about twice as big. So I'm going to say that they correspond to 2. We could actually do the math on this. So in order to do the math, we would find the smallest number, which is this 54, and divide everything else by that 54, but I'm just eyeballing it. Now this is should be giving me the total number of hydrogen atoms, which is 1, 2, 3, 4, 5, 6, 7, 8. And I can match that up with my molecular formula just to kind of verify that I'm on the right track. So things are looking good. So peak number 1 and 2 and 3 and 4 1, 2, and 3 and 6 all have 1 hydrogen, and peaks 4 and 5 correspond to 2 hydrogens. And we've got, in terms of splitting, I've got some zoomed in. Here is peak number 1, and it is a doublet. And here's the rest of them. Peak number 2 also looks like a doublet. Peak numbers 3 and 4 look like singlets. Peak number 5 is kind of maybe it's a triplet. It's just really messy. And then peak number 6 is a quartet. I'm going to write that as a fortet because Q is quartet or quintet. Another thing we should be looking at are the peaks that are in this area right here. These are the peaks that correspond to the benzene ring. 2, 3, 4, and 5. 2, 3, 4, and 5. These are the benzene hydrogens. So this gives us some information about how many hydrogen atoms are on the benzene ring. 1, 2, 3, 4, 5, 6. That's impossible. So one of these must be kind of a rogue peak that ended up in that particular spot. That's not going to be very useful to us. At most, we could only have 5 peaks on the benzene ring. So not a whole lot of information that's going to come out of this. The one thing that I am seeing on this that is kind of interesting to me, this peak that's all the way out here, like this far, this is going to either typically be an aldehyde or a carboxylic acid. And so I'm wondering if maybe I have an aldehyde. I'm pretty sure that I don't have a carboxylic acid because the carboxylic acid functional group has the OH group, and I definitely would have seen that in the IR. But maybe I have the aldehyde. I am, pretty bad about spotting aldehydes when I look at the IR. So when I go back and look at the IR again, if I have an aldehyde, I would have peaks around, I would expect to see peaks around 2,700, and I don't see that. But I do have these 2 peaks right here. 29 and 3,000. Maybe it is an aldehyde. It might be. This peak, this little guy out here though is something I need to pay attention to. So maybe I have an aldehyde. Not totally sure. Okay, so next thing we want to look at the carbon NMR. Here it is, and again I've got some peaks that are kind of jammed up together, so I have a zoomed in version of what that looks like. This is between 120 and 140. So between 120 and 140, I have 1, 2, 3, 4, 5 peaks. And that's giving me these guys right here. So there are a total of 5 peaks in this area. That was between 120 and 140. And then I've got 2 more peaks on here. So that means that I have a total of 7 types of carbon. And my formula was C9H8O. Propose at least one structure for my unknown. Well, I know for sure that I have a benzene ring, something that looks like that. I need to have an additional 3 carbons coming off of that benzene ring. I'm just going to put them all together. I need to have a carbon-oxygen double bond. Let's just kind of keep going with this idea that I have an aldehyde. So I'm going to give myself an aldehyde right there. And then remember, I need to have one more site of unsaturation. I came up with an HDI of 6. So I've got my 1, 2, 3, 4, 5. I need one more site of unsaturation. The only place I could fit it in this particular structure would be right here. Now, I'm not necessarily saying that this is my molecule. I'm just proposing a structure. I'm just brainstorming. Like, I know for sure I've got a benzene ring. I know for sure I have a carbonyl group. I feel like maybe I have an aldehyde, and I know I've got at least one more site of unsaturation. This is giving me a total of 9 carbon atoms and 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. So this is consistent with my data. I don't know for sure that that's what I've got. What I need to do now is go to NIST and see what my actual structure is. So what I'm going to do is pull up the NIST website. And what we're looking for specifically is called the Webbook. So I'm going to actually get even more detailed here. NIST Webbook. And on here, we're going to search by formula because that is the one thing that we know for sure about this molecule. C9H8O. Make sure you type in an O and not a 0. And we're just going to go. Now it's going to give us a list. I'm not exactly sure what the order is with this particular list, but here it is. And what I'm going to do is I'm not going to specifically look for this molecule right here, but I am going to look for something that is similar to it. So notice this little guy down here, this number 4, not very similar. But anything starting at the top, number 1, that molecule right there, it looks pretty similar to the one that I proposed. You might be wondering what's going on with this weird bond, and that's just accompanying E versus Z notation all in one. It's not necessarily specifying a particular isomer. So I'm going to click on this guy, and you can see here that it's wanting to kind of distinguish it between the 2 different stereoisomers. Maybe I don't really want to waste my time with that. Like maybe I want to look specifically at the E and the Z. So this is the same as the one that I drew. And what I'm going to go down to is the phase change data. This is going to give me my boiling point, 521 versus 524. That's really, really similar. I feel like that's probably a match, and that's only off by a couple degrees. I'm just going to kind of look at the other one out of curiosity. Phase change. This one doesn't even have phase change data. If it doesn't have it, it's probably not what you have. Yeah, I mean, I feel like this was really close, the boiling point. So let's explore a little bit more. Since we got a pretty good match for our boiling point, it doesn't match perfect, but it is very similar. Let's compare the spectra. The other spectra that we have, all that we have is a mass spec. Note that it may not have all 4. Usually it does, but this one only has a mass spec. So I'm going to pull up NIST's mass spec and look at that. That actually is a really good match. I'm going to pull my own mass spec back up again just so that we can see it. But remember the issue that I had with trying to decide which was the parent peak? Same thing. We can see the same thing here. These do look extremely similar. They're not exactly the same. Look at like the small peaks that are present between 100 and 120, and we don't have those in ours. But if we're looking at the main peaks, really almost identical, really similar. So I feel really confident that this is what my unknown is. Like I feel like I've identified it. And so once you know what your unknown is, or you believe you know what your unknown is, you're going to enter the name of the unknown into the software. Now, the software is only set up to accept one particular name, and as you know, there are a lot of different names for different molecules. So you could type this in. You should have the E in front of the name. You should type it in as E, cinnamaldehyde, if this was your unknown. And it might tell you, oh, that's actually wrong. It's supposed to be some other synonym for that molecule, like one of these other names. But that doesn't really matter because I'll be able to tell when I grade your assignment, I'll be able to tell that you got it right. So maybe it's going to say, nope, you're wrong. It's actually trans cinnamaldehyde. And it's the same thing. Just the software isn't smart enough to know the difference.